Hide your wife, hide your kids, hide your wife, hide your kids, hide your wife, and hide your husband, cause they bring your name money out here. You don't have to come and confess. We're looking for you. We gon' find you. We gon' find you so you can run and tell.
Okay, everyone, welcome to lesson 2.3 on some applications of vectors and dot product, etc. We're going to be talking today about velocity and work. I think today is going to be a short video, and I apologize in advance for the frog in my throat. So based on our discussions in Unit 1, we defined velocity as a vector because velocity has magnitude, and that magnitude is the speed of whatever it is we're looking at, and velocity also has direction. So today we're going to look at some harder velocity problems. Let's start by an example. If a plane has some velocity that we'll call vector v, and it meets a wind with velocity w, let's try and draw a diagram to determine the resultant velocity. So physically, if I have my plane traveling in some direction with some velocity, label it like that, and as this plane is traveling, it meets a wind, velocity w. So this wind is acting on the plane, and logically we can guess that this wind is going to push the plane over to the right a little bit. What I've drawn as my setup is called a position diagram. We want to take this and we want to draw a diagram. We want to take this position diagram and we want to draw a diagram that will show us the resultant velocity. So we can imagine again this plane traveling at some velocity v. And it's going to meet this wind, and so we're going to add the velocity of the plane and the velocity of the wind, and what we get will be a vector that represents the velocity of the plane plus the velocity of the wind. This is the resultant velocity. It's also what we've drawn. It's called a vector diagram. So then let's apply this to a harder velocity problem. Here I have a boat that's heading 15 degrees west of north with a speed of 12 meters per second. We want to determine its resultant velocity when it meets a 5 meter per second current from 15 degrees north of east. So I'm going to start by drawing almost like an axis, and this is going to represent my compass. North, south, east, and west. So my boat is traveling 15 degrees to the west of north. So my boat's going to be traveling in a direction like this, with the angle between north and the vector being 15 degrees. Okay, so we can see that angle between the line representing north and the vector is a 15-degree angle. And here comes the tricky part in the wording of the question. This boat meets a current current that's coming from 15 degrees north of east. So a common mistake people make is drawing a vector acting on this boat that's at an angle of 15 degrees to the north of east. And that's wrong. Based on the wording of this question, the current is coming from that direction, so it's pointing in the opposite direction of what I just drew. It's coming from that direction. So again, I'm going to draw in my set of axes to represent my compass. And I can imagine this current acting on the boat, and it's meeting that boat at a 15-degree angle. Just zoom in a little bit. So I can see the vector head of my current is interacting with the vector head of the boat, and they're meeting at a 15-degree angle. What I need to do is take this position diagram that I've drawn and turn it into a vector diagram by taking the current and adding it to the head of the vector for the boat. So what we're looking for, that line there, if we call the velocity of the boat and the velocity of the current, we'll call that vector c, and then this line would be the vector v plus c. To find the angles in here, we need to try and find one of the angles at least to start solving this triangle. We need to think about our rules for angles and parallel lines. If this is a 15-degree angle here, that would make this angle also 15 degrees. I see a Z pattern here to here. This angle would be 15 degrees. The angle between south and west is 90 degrees. So if I call this point here angle A is going to be a 90-degree angle minus this 15-degree angle. So 90 minus 15, and then plus this 15-degree angle here. So it just so works out that angle A is a perfect 90-degree angle. So this is going to make our problem solving a little bit easier. Let me redraw this diagram without all the dotted lines. So I have a 90-degree angle. I know the length of this side, the magnitude of this side is 12. That's the velocity the boat's moving at. And the magnitude of this side is 5. So the magnitude of vector v plus c you can find by using Pythagorean theorem. So the magnitude of v plus c is going to be the square root of 144 plus 25, which is exactly 13. So the magnitude of v plus c is 13. I also need to find its direction, so I can find this angle, theta, by again using some trigonometry. I'm going to use the tangent ratio, so the tangent of angle theta is equal to 5 over 12, which means that theta will be the inverse tangent of 5 over 12. If you plug this out on your calculator, that works out to about 22.6 degrees. So I know the magnitude of this vector, I know the angle relative to the vector diagram, but I don't know the angle as a compass bearing. So I need to give this velocity of bearing. I do know initially the boat was moving at a 15-degree angle, 15 degrees north of east. Sorry, 15 degrees do know that the boat was initially moving 15 degrees west of north. I can find my new bearing by taking my theta and adding 15. So 22.6 plus 15, I end up with an angle of 37.6. So just to end this question, a little therefore statement. The velocity is 13 meters per second. And then I'm traveling north 37.6 degrees to the west. Unfortunately, my voice is failing me. So I did want to do some work with some physical applications of the dot product. That's going to have to wait till class tomorrow. We're going to specifically be looking at some ways that dot product can be applied to physics and solving some problems in physics. Okay, thanks for watching.